When rail fans talk about modern locomotives, they talk about the Dash 9. When railroads talk about reliability, they talk about the AC-4400. And when engineers talk about efficiency, they talk about the GEVO. But what they rarely talk about is the machine that made all of them possible. Not the fastest, not the strongest, but the one that changed how locomotives are built. This is the story of the GE-8, the quiet revolution. If you look at any modern freight railroad today, you'll see descendants of a design philosophy that began in the mid-1980s. A philosophy built not around raw power or dramatic innovation, but around something far more valuable to struggling railroads: reliability through simplicity, serviceability through standardization, longevity through intelligent engineering. The Dash 8 family wasn't born in a vacuum. It emerged at a moment when American railroads were fighting for survival, when deferred maintenance had become a crisis, and when the old ways of building locomotives simply weren't working anymore. GE recognized this moment and responded not with revolutionary technology, but with revolutionary thinking about how locomotives should be designed, built, and maintained. In the decades since, the Dash 8 has become almost invisible in discussions of railroad history. It's overshadowed by its more famous successors, overlooked in favor of more dramatic stories. But for those who understand railroad operations, who know what it takes to keep trains moving day after day, the Dash 8 represents something profound, the foundation upon which modern freight power was built. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand why the Dash 8 mattered, you need to understand the American railroad industry in the early 1980s. This was not a time of prosperity or confidence. This was a time of survival. The freight railroad industry was emerging from one of the darkest periods in its history. The 1970s had been catastrophic. Penn Central's collapse in 1970 had sent shockwaves through the industry, proving that even the largest railroads could fail. Bankruptcies cascaded through the Northeast and Midwest. Rock Island, Milwaukee Road, Erie, Lackawanna. Names that had defined American railroading for over a century were disappearing. By the early 1980s, the railroads that survived were operating on razor-thin margins. Deferred maintenance wasn't just a problem. It was a way of life. Locomotives that should have been retired decades earlier were still hauling freight because railroads couldn't afford replacements. Track that desperately needed rehabilitation was left to deteriorate because there was no capital for improvement. Yards were filled with dead locomotives waiting for parts that might never come. The locomotives themselves reflected this crisis. The EMD SD-42, which had become the industry standard in the 1970s, was a magnificent machine in many ways. But it was also complex, demanding of maintenance and expensive to keep running. When something went wrong with an SD-42, diagnosis could take hours. Repairs often required specialized knowledge. Parts had to be ordered and shipped. A locomotive might sit in a shop for days or weeks, waiting for a single component. For railroads operating in the economic conditions of the early 1980s, this was unsustainable. They needed locomotives that wouldn't break down. They needed machines that could be diagnosed quickly when problems did occur. They needed designs that didn't require a team of specialists to maintain. They needed, above all, locomotives that would keep moving freight even when everything else was falling apart. GE saw this moment clearly. While EMD continued to refine their traditional approach to locomotive design, GE recognized that the market had fundamentally changed. Railroads weren't buying power anymore. They weren't buying speed or capacity. They were buying survivability. The question GE asked wasn't, how do we build a more powerful locomotive? It was, how do we build a locomotive that railroads can actually afford to operate? How do you design a machine that can remain in service with minimal downtime, that requires fewer specialized technicians, that can diagnose its own problems, that lasts longer before major overhaul? This thinking drove every aspect of the Dash 8's development. GE wasn't trying to win a horsepower war. They were trying to solve a fundamental economic problem facing their customers. They were designing a locomotive for railroads that were broke, understaffed, and desperate for machines that would simply work. The Dash 8 became GE's answer to an industry in crisis. It was built for railroads trying to rebuild from bankruptcy, for maintenance departments operating with skeleton crews, for dispatchers who needed consistent, reliable power to keep freight moving on tight schedules. For CFOs who needed to know that their locomotive fleet wouldn't drain what little capital they had left. This context, this moment of desperation and transformation in American railroading, shaped everything about what the Dash 8 would become. It wasn't designed to impress, it was designed to endure. The Dash 8 represented a fundamental shift in how GE approached locomotive construction. This wasn't just about building a better engine or improving electrical systems. This was about reimagining the entire process of how a locomotive is manufactured, serviced, and maintained throughout its life. GE's core insight was deceptively simple. A locomotive should be assembled like a series of integrated modules, not hand-built like a custom machine. Think of it as the difference between building a car in a modern factory versus building one in a craftsman's garage. Both can produce excellent results, but only one can. Be maintained efficiently by crews in the field. The modular philosophy touched every aspect of the Dash 8's design. Wiring harnesses, for instance, were standardized and pre-assembled. Instead of routing hundreds of individual wires through the locomotive during construction, entire harness assemblies were built on benches, tested, and then installed as complete units. This meant that in the field, a damaged harness section could be unbolted and replaced in hours rather than days of tracing individual wires. Electronic systems followed the same principle. The Dash 8 introduced bolt-on electronics racks that could be accessed from outside the locomotive without entering confined spaces. Control boards were mounted in removable modules. Diagnostic systems were designed as plug-and-play components. A technician didn't need to understand the intricate details of every circuit. They needed to identify which module was faulty, unbolt it, and install a replacement. This approach extended to the locomotive's major mechanical systems as well. Traction motors used standardized mounting points. Cooling system components were designed for quick removal. Air brake equipment followed consistent layouts across the entire Dash 8 family. A mechanic trained on a Dash 840B could service a Dash 840C without relearning everything from scratch. The implications of this design philosophy were profound. For railroads, it meant dramatically reduced shop time. A locomotive that might have spent 3 days in maintenance under the old approach could now be back in service in 1 day. It meant smaller parts inventories, because the same modules were used across multiple locomotive models. It meant lower training costs, because mechanics could learn standardized procedures rather than locomotive-specific techniques. For GE, it meant more efficient production. Assembly lines could move faster when workers were installing pre-built modules rather than custom-fitting components. Quality control improved because modules could be tested before installation. Updates and improvements could be rolled out across the entire fleet by simply swapping modules rather than retrofitting individual locomotives. This modular approach also had implications for the Dash 8's evolution over time. As technology improved, GE could upgrade specific systems without redesigning the entire locomotive. Better diagnostic computers could be installed in the same racks. Improved cooling systems could bolt into the same mountings. The basic architecture remained stable while the components inside it evolved. The philosophy extended beyond the hardware to the software and control systems as well. The Dash 8 was among the first GE locomotives designed with the assumption that control logic would be updated and improved over the machine's lifetime. Early versions ran relatively simple control algorithms, but the architecture allowed for increasingly sophisticated software as it became available. Looking back, this modular philosophy proved to be one of GE's most important innovations. It became the foundation for every GE locomotive that followed. The Dash 9 expanded on it. The AC 400 refined it. The Evolution series took it to new levels of sophistication. But the core insight, that locomotives should be designed as integrated systems of replaceable modules, originated with the Dash 8. This wasn't the kind of innovation that generates headlines or wins engineering awards. It was invisible to everyone except the maintenance crews who had to keep these machines running year after year. But for them, it changed everything. The Dash 8 represented the moment when GE stopped building locomotives like custom machines and started building them like modern industrial equipment. And that shift, more than any specific technical feature, set the stage for everything that came after. While the modular philosophy defined the Dash 8's overall approach, a number of specific engineering innovations distinguished this locomotive family and influenced decades of subsequent designs. These weren't always the most obvious features, but they represented genuine advances in reliability, maintainability, and operational capability. The wiring architecture of the Dash 8 marked a significant departure from previous practice. Earlier GE locomotives like the Dash 7 series used what could only be described as spaghetti wiring, hundreds of individual wires routed through the locomotive, each one potentially a point of failure. Tracing a fault in such a system could take hours or even days. The Dash 8 introduced grouped harness bundles, with each bundle color-coded, heat-resistant, and pre-terminated at the factory. More importantly, these harnesses were routed through dedicated cable trays with logical organization. Power circuits ran separately from control circuits. Signal wiring was isolated from high-voltage systems. Each harness was documented with clear schematic diagrams that matched the physical installation. For maintenance crews, this transformation was revolutionary. A problem with the dynamic brake system? Check the green harness in the number 3 cable tray. An issue with traction motor control? The blue harness in cable tray 7. What had once required experienced electricians with intimate knowledge of locomotive wiring could now be diagnosed by technicians with a schematic and a multimeter. This wiring architecture became the standard for all subsequent GE locomotives and significantly reduced troubleshooting time throughout the industry. The dynamic brake system on the Dash 8 incorporated what GE called blended braking, an early implementation of coordinated dynamic and air brake control. The concept was straightforward, but the execution was complex. As a train descended a grade, the locomotive's computer would continuously calculate the optimal mix of dynamic braking and air braking to maintain the desired speed, while minimizing wear on both systems. The benefits were multiple. Wheel wear decreased because dynamic braking handled more of the load. Brake shoe replacement intervals extended. More significantly for train handling, the reduction in air brake application meant less slack action in long freight trains. Anyone who's ridden in the cab of a freight locomotive knows the constant jerking motion as slack runs in and out through a 100-car train. The Dash 8's blended braking system smoothed this motion, reducing stress on couplers and making trains easier to handle on mountain grades. Cooling systems received significant attention in the Dash 8 design. GE engineers completely redesigned the forced air cooling for the main alternator, addressing a persistent problem in earlier locomotives. Under sustained heavy loads, particularly on long mountain grades, alternator temperatures could climb to dangerous levels, forcing crews to reduce power or shut down temporarily. The Dash 8's redesigned cooling system used larger fans with improved airflow patterns, better ducting to direct air precisely where it was needed, and revised alternator ventilation passages that reduced hot spots. The result was a locomotive that could maintain continuous full power output for extended periods without overheating, a critical capability for Western railroads operating in the Rockies or Sierra Nevada. Structural engineering on the Dash 8 included several improvements that weren't immediately visible but proved important for longevity. The underframe received reinforced end sills, the heavy steel structures at each end of the locomotive that absorb coupling forces. These reinforced sills reduce frame flex by approximately 25% compared to the Dash 7 series, which meant less fatigue stress on the frame over time and reduced cracking around mounting points for traction motors and trucks. This structural reinforcement also improved crashworthiness. In an era before wide-nose safety cabs became standard, the Dash 8's stronger frame structure provided additional protection for crews in the event of a collision. It wasn't a safety cab, but it was a step in the right direction. Perhaps the most forward-looking innovation in the Dash 8 was its integrated control logic, an early version of the sophisticated computer control systems that would dominate modern locomotives. Earlier GE locomotives had used discrete electrical controls with minimal computer integration. The Dash 8 moved toward centralized digital control, with a computer system managing throttle response, load distribution, and fault monitoring. This control system enabled smoother power transitions. When an engineer advanced the throttle, the computer managed the resulting increase in generator load, traction motor current, and cooling system response to avoid surges and optimize fuel consumption. The result was more consistent acceleration and reduced fuel spikes during power changes. More importantly, this control architecture provided the foundation for increasingly sophisticated systems in later locomotives. The high adhesion software in the Dash 9, which dramatically improved traction control, built directly on the Dash 8's control framework. The Trip Optimizer system in the Evolution series, which uses GPS and terrain data to optimize throttle settings, descended from these early attempts at intelligent locomotive control. The Dash 8 also introduced improved electrical load management. In earlier locomotives, auxiliary systems, cooling fans, air compressors, battery chargers drew power somewhat independently, which could create situations where auxiliary loads competed with traction loads during peak demand. The Dash 8's control system prioritized and sequenced these loads more intelligently, ensuring that traction always had priority while still maintaining adequate auxiliary power. These engineering innovations weren't revolutionary in isolation, but collectively they transformed the reliability and capability of freight locomotives. More importantly, they established patterns that GE would refine and expand in subsequent decades. The modular wiring, the integrated control systems, the emphasis on cooling and thermal management, the structural reinforcement. All of these became standard features in modern locomotives, traced back to innovations first implemented in the Dash 8 family. The true measure of any locomotive isn't found in specification sheets or engineering drawings. It's found in how the machine performs in daily service, how it affects the people who operate and maintain it, and how it changes the economics of railroad operations. By these measures, the Dash 8 proved transformative. Dispatchers, who coordinate train movements across entire subdivisions, noticed something interesting about Dash 8-powered trains. They were more predictable. Wheel slip alarms, which had been a constant irritation with earlier locomotives, occurred less frequently. The Dash 8's improved wheel slip control meant trains maintained more consistent speeds, particularly when starting heavy loads or accelerating on grades. For dispatchers trying to maintain tight schedules on busy main lines, this consistency was invaluable. A train that moves at a predictable pace is far easier to slot into a scheduling plan than one that might lose 10 minutes to wheel slip and then make it up with aggressive running later. The fuel-saving logic in the Dash 8's control system produced similar operational benefits. Earlier locomotives required constant throttle adjustment to maintain speed, what locomotive engineers call throttle jockeying. The Dash 8's computer-managed power delivery smoothed this out considerably, maintaining speed with smaller, less frequent throttle movements. Engineers reported that Dash 8s simply felt smoother to operate, particularly in the 40 to 50 mile per hour range typical of heavy freight service. This smoothness wasn't just about comfort. Smoother power delivery meant less stress on drawbars and couplers throughout the train. It meant fewer broken knuckles and parted trains. It meant merchandise that arrived with less damage from the constant jerking of poorly controlled acceleration. These might seem like minor details, but multiply them across thousands of trains and millions of miles, and they represent substantial operational savings. Mountain railroad operations saw particular benefits from the Dash 8. Early tests on steep grades demonstrated that Dash 8s could handle assignments that previously required helper locomotives. The combination of improved cooling, better adhesion control, and more consistent power output meant a Dash 8 could haul tonnage up grades that would have overwhelmed earlier locomotives. For railroads operating in the Rockies, the Appalachians, or the Sierra Nevada, this translated directly to reduced operating costs. Maintenance departments, always the ultimate judges of locomotive quality, gave the Dash 8 high marks. The key metric was mean distance between failures, how many miles a locomotive could run before something broke that required shop attention. Early Dash 8s were consistently running 20,000 miles or more between shop visits, compared to 15,000 or less for many earlier designs. That difference might not sound dramatic, but it meant roughly 30% fewer shop visits over a locomotive's annual mileage. When Dash 8s did require maintenance, the modular design proved its worth. Diagnosis time dropped dramatically. A problem that might have taken 6 hours to isolate in a Dash 7 could often be traced in 2 hours or less in a Dash 8. The standardized wiring and modular component racks meant technicians spent less time hunting for problems and more time fixing them. Shop superintendents reported that Dash 8s moved through regular maintenance cycles faster than any previous GE locomotive. The reduction in sudden electrical failures was particularly significant. Earlier locomotives had a frustrating tendency to develop mysterious electrical problems that would ground a unit until a skilled electrician could spend hours tracing through complex wiring. The -8's organized wiring and improved diagnostic systems drastically reduced these incidents. When electrical problems did occur, they were typically confined to a specific module that could be quickly identified and replaced. Railroads began using -8s for their most demanding services. High-priority UPS intermodal trains, running on tight schedules with severe on-time penalties, were often assigned -8 power. Auto-rack trains carrying new vehicles from manufacturing plants to distribution centers ran behind -8s. Time-sensitive manifest trains loaded with expedited freight got -8 consists. These assignments reflected railroad confidence that the -8 would deliver reliable, consistent performance when it mattered most. Some railroads, experimented with -8s on what were called high-speed freight corridors, main lines upgraded for sustained speeds above 50 miles per hour. The -8's smooth power delivery and stable suspension made it well suited for these faster operations. While freight locomotives would never match passenger train speeds, the ability to run consistently at 55 or 60 miles per hour on suitable track opened new possibilities for time-sensitive freight services. The -8 also proved valuable during the labor shortages that affected many railroads in the late 1980s and early 1990s. The locomotive's reliability meant railroads could operate with smaller rosters. Instead of keeping extra locomotives on hand to cover for units in the shop, railroads could run tighter fleets with greater confidence that their power would be available when needed. This improved asset utilization had direct impact on return on investment calculations. Crew opinions varied, as they always do, but a common theme emerged. -8s were honest locomotives. They didn't have mysterious quirks or unpredictable behavior. The controls responded consistently. The throttle did what you expected. The brakes worked predictably. For engineers responsible for hundreds or thousands of tons of freight moving at high speed, this predictability built confidence. You knew what the locomotive would do, and that knowledge made your job easier and safer. It's worth noting what didn't change. The -8 didn't revolutionize railroad operations overnight. It didn't enable radically new service patterns or transform the economics of freight transportation by itself. What it did was make existing operations work better, more reliably, more efficiently, more predictably. And in an industry where margins are thin and reliability is everything, that made all the difference. The -8 family included several unusual variants and experimental models that reveal the evolution of GE's thinking during this period. These rare locomotives often represented transitional technologies or specialized applications that never achieved widespread production. The C328 stands out as perhaps the most unusual production -8. Conrail ordered just 10 of these locomotives in 1984, making them among the rarest standard-gauge mainline diesels in North America. The C328 used a 3,100 horsepower version of the 7FDL engine, an odd power rating that fell between the more common 3,000 and 3,600 horsepower models. Conrail's intention was to test whether this intermediate power rating offered advantages for their specific service requirements. It didn't. The C328s developed chronic overheating problems, particularly during summer operations in the hot, humid conditions of Conrail's eastern territory. The engine's cooling system, essentially adapted from the lower-power -7 series, couldn't adequately handle the thermal load of the higher-output engine. Conrail crews disliked them, maintenance departments struggled with them, and the entire class was retired after relatively short service lives. The C328 experiment demonstrated the importance of matching cooling capacity to power output, a lesson GE applied to subsequent -8 designs. GE's Erie testing facility operated several -8 test locomotives that rail fans occasionally spotted but rarely photographed. These units, painted in plain gray or blue primer rather than any railroad livery, incorporated experimental hardware that GE was evaluating for production locomotives. Some tested alternative cooling fan designs. Others experimented with different traction motor configurations. A few apparently served as electrical test beds for the control systems that would later appear in the -9. These grayback locomotives led obscure lives, rarely leaving the eerie test track and spending most of their time pulling dynamometer cars in repetitive testing cycles. When their experimental equipment was no longer needed, they were often rebuilt into standard production models and sold to railroads, their unusual origins hidden under fresh paint and new road numbers. Mexican railroads received specially modified Dash 8s designed for the high-dust environments common in northern Mexico. These locomotives featured redesigned air intake systems with enhanced filtration to handle the fine desert dust that plagued locomotive operations in arid regions. The intake grills had a different appearance than standard Dash 8s, with multiple stages of progressively finer mesh screens. Cooling systems received additional protection against dust infiltration, and cab filtration was significantly improved to protect crews and electronic equipment. These modifications proved successful enough that some U.S. railroads operating in the desert Southwest adopted similar filtration systems for their own Dash 8 fleets. The Mexican export variants demonstrated how the Dash 8's modular design philosophy allowed for regional customization without requiring complete locomotive redesigns. Australian Dash 8 derivatives represent some of the most extensively modified versions of the basic design. Australian railroads operate on multiple different track gauges, including narrow gauge systems that required significant modifications to standard North American locomotive designs. National Rail and Queensland Rail both operated Dash 8-based locomotives adapted for narrow gauge operation. These adaptations required more than just different truck spacing. The entire locomotive had to be reconfigured to maintain proper weight distribution and center of gravity on the narrower gauge. Cooling systems were rearranged to fit the more constrained underframe space. Cabs were modified to lower profile designs to meet Australian clearance requirements. Electrical systems were adapted to Australian standards. The result was a locomotive that retained the Dash 8's core engineering principles while looking distinctly different from its North American cousins. Canadian National and Canadian Pacific ordered early wide-nose experimental Dash 8s that predated the standard North American safety cab design. These locomotives featured what CN called comfort cabs, wider nose sections with improved visibility and crash protection compared to standard narrow nose designs, but not yet the full wide nose configuration that would become standard in the 1990s. These experimental cabs had non-standard window shapes and different door configurations than later safety cabs. They represented GE working with Canadian railroads to develop improved crew protection while maintaining compatibility with existing maintenance facilities and operating practices. The lessons learned from these experimental installations directly influenced the wide-nose cab design that eventually became standard across the North American industry. Some railroads received Dash 8s configured for specialized service that required unusual modifications. BC Rail, operating in the rugged terrain of British Columbia, specified enhanced snow plowing equipment and additional cold weather protection. Guilford Rail System, running through the New England states, ordered units with specific paint schemes and radio equipment to match their unique operating requirements. Various leasing companies took delivery of Dash 8s painted in distinctive corporate colors, often with simplified control stands and interiors designed for operation by crews from multiple different railroads. These variants and oddities illustrate an important aspect of the Dash 8 story. While the locomotive established standardization and modularity as core principles, it also demonstrated flexibility in meeting specific customer requirements. GE could modify the basic design to suit particular applications without abandoning the fundamental architecture that made the Dash 8 practical and maintainable. This balance between standardization and customization became another lasting legacy of the Dash 8 program. The Dash 8 didn't dominate headlines. It didn't break speed records. And it didn't become a cultural icon like the streamliners of the passenger era or the early diesels that displaced steam. But in the background, quietly and steadily, it changed how locomotives are designed, built, repaired, and operated. When GE developed the Dash 9 in the early 1990s, they built upon the modular architecture established by the Dash 8. When they created the AC4-400, it inherited the Dash 8's emphasis on maintainability and standardization. When the Evolution series arrived with its sophisticated emissions, controls, and fuel economy, it relied on control system architectures that trace back to the Dash 8's integrated logic. The modern GE locomotive, whether it's an ET/AC hauling containers across the Southwest or an ES-44DZ moving coal through Wyoming, exists because the Dash 8 proved that reliability and maintainability could be designed into a locomotive from the ground up. That these qualities didn't have to be accidents of good engineering, but could be systematic features of how a locomotive is conceived and constructed. The railroads that ordered Dash 8s in the 1980s were often struggling financially, facing uncertain futures, and desperately needing locomotives that would simply work. GE gave them exactly that. Not the most powerful locomotives, not the most technologically advanced, but machines that would start reliably, run consistently, and return to service quickly when maintenance was needed. In doing so, GE helped keep freight moving through one of the most challenging periods in American railroad history. The mechanics who maintained Dash 8s, the engineers who operated them, and the dispatchers who scheduled them might not have realized they were witnessing a fundamental shift in locomotive design philosophy. They were too busy doing their jobs, moving freight, keeping the railroad running. But looking back, we can see what was really happening. An entire approach to locomotive engineering was being transformed, moving from custom machines requiring specialized knowledge to standardized systems that could be maintained efficiently by regular maintenance crews. Without the Dash 8, there is no Dash 9, no AC-4400 CW, no Evolution series, no foundation for the computer-controlled, emissions-compliant, fuel-efficient locomotives that dominate modern freight service. The Dash 8 was the locomotive that reshaped an industry, not by force, but by foundation. It proved that sometimes the most important innovations aren't the ones that grab attention. Sometimes they're the ones that quietly change how everyone does their work, establishing new standards that become so fundamental that future generations forget there was ever another way. That's the real legacy of the GE-8. Not glory, not headlines, not records. Just the steady, reliable foundation upon which an entire generation of freight power was built. The quiet revolution that changed everything.